In the 1940s, Arthur Iberall began observing an area of physics that was neglected, that of complex systems with their very long internal factory day delays. Iberall, along with Harry Soodak, was able to turn keen observations into a new field of the physics of complex systems. They called it Homeokinetics, from the Greek meaning similar movement. This is in contrast to homeostasis, which defines stability arranged around a set point. In homeokinetics, stabilities emerge from interacting processes. Normal physics, or flatland physics, deals with the processes at single levels. Homeokinetic physics combines flatland physics with the study of the up-down processes that binds the levels. The approach models the entire universe of atomistic-like units bound in interactive ensembles that form systems, level by level, in a nested hierarchy. Tools such as mechanics, quantum field theory, and the laws of thermodynamics provide key relationships for the binding of the levels, how they connect, and how the energy flows up and down. Homeokinetics treats all complex systems on equal footing, both animate and inanimate, providing them with a common viewpoint. The complexity in studying how they work is reduced by the emergence of common languages for all complex systems. At least two scientists are needed, one who is versed in physics and irreversible thermodynamics. The other is trained in the specialty. A person is a system bounded in time and space from above and below. Skin is the border separating the inside from the outside. The person's life is bounded in time from birth to death. When the person gets into a car, the person and the car become another system. The car joins other cars and loses their autonomy. The flow of cars in a traffic system is much like the flowing of blood cells through our veins. An atomism is a limited object of any size which is largely repeated in structure and character. It can withstand forces of interaction up to some level without permanently deforming, yet it can bind with some of its counterparts. It can possess and share mass, energy, momentum, or electric charge. When the actors move, they interact with other actors. Two people see each other in a bar, walk over, talk, and then perhaps dance together. Two cars avoid a collision by veering away from each other. The actors are engaging in a game which may be called banging into each other by pairs. Forces guarantee that the actors will bang into each other. A few major things are conserved during this game, such as the sum of paired mass or matter, energy, momentum, and electric charge. A system is a group of relatively common atomisms organized into a high-ordered atomism bounded from above and below in the space and time domain. In simple systems, when atomisms bang into each other, after a few interactive collisions, they are brought to equilibrium. For complex atomisms, their interior movements are organized into very, very long time-delayed patterns as countable by external bangings, thousands, millions, trillions. If you eat a cookie and you do not see the resulting action for hours, that is complex. If boy meets girl and they become engaged for a protracted period, that is complex. If a foreign leader tears up a treaty and a government takes days to respond, that is complex. The purpose of the action is to tell the story of the collective. For a group of molecules in a balloon, the story of the collective may be to form a gas. As a result of playing the game, by sharing of motion through their conservations, they all achieve the same temperature, or essentially the same energy. Now, if you want to face them, you will have to face them as a collective. You are no longer dealing with single atomisms. How can one know that? Somebody can aim that balloon at someone else and blow them away. At a collective level, the story of the collective force is the social pressure. One can tell a human army, a gang, or a group to go kill or go build a nation, and the bunch will walk out together and act no longer as individuals, but as a collective. Let's look inside and define a complex system. Systems involve movement and change, and so do complex systems. What is different in complex systems is the long time delayed internal processes that are taking place. They comprise a factory of processes which are, for the most part, long drawn-out flow processes. We say that they are involved in a complex cascade of energetic processes pouring into and through the field system at very many time and process scales. Complex systems have very extended time scales among their atomistic processes. They have extensive field memory functions spread out in time and space. Complex systems can use any material or energetics for memory functions, so they are physical-chemical by nature. In the living body, storage is commonly seen as short-lived and long-lived molecules. The memory functions are the factory processes. Complex systems appear to direct their activities almost with purpose. They use languages. Language is the small matter-energy catalysts that switch or evoke states of action. We speak to our organs, our cells, and to each other, and that controls the flow of our collective actions both in space and in time. The key homeokinetic problem is how the bottom collective structure and functions is connected to the functionally remote character of the top collective. We are fortunate that the physical game played by nature is and has to be indefinitely repetitious. It is only because of that we can deal with the many forms of those games by attempting to recognize the repetitions. We can deal with the physics of complex systems because we can recognize their conservations. Let us look for repetitions in the complex atomism known as a human being. At a first rudimentary level, one takes a breath, then one takes another breath, and so on and so on. As long as breath follows breath and heartbeat follows heartbeat, some of the fundamental internal machinery is working. Note that the process starts out of the momentum and the movements of the heart, the lungs, and the other organs. At the bottom of this, there still remains only momentum, energy, matter, and electric charge. But let's jump to a more integrative level. There's more to see over the day. The organism has searched for and acquired food, slept, moved, drunk fluids, voided, and interpersonally interacted with its fellow organisms. There's much more machinery involved at this level. But notice, more or less, one day is like another. This is still not quite integrative enough. There are other machinery processes, such as water balance over 3 days and the female menstruation cycle. But engraved within the body's machinery, there is more nearly a yearly scaling of processes. Let us imagine wandering around inside your body, a city, a civilization, or a galaxy. It will always look like a giant busy play. All you will see are pieces moving in and out of a great number of stations. Activities and processes are continually moving on. It isn't until a great number of steps have taken place at some or all of the stations that what is going to emerge becomes apparent as a product or a message, that you know that Act 1 of the play has taken place, or that an inning has been played. What emerges from the material energetic transformations are only such high-ordered products or messages made up of the same kind of material energetic processes we see in the simplest of systems. A transporting diffusion is added, a diffusion into internal action. That diffusion measure is called the associational or bulk viscosity. Here is where the long time delay lies, which makes for complexity. It is only a complex system if the complex patterns it displays repeat again and again and again. To study the complex system, our job is to recognize the repetitions and also recognize the conservations. Complex systems repeat their entire spectrum of performance over some characteristic period, referred to as their factory day. This is a period that is long compared to the time scale for atomistic interactions. You cannot run a factory if every component at every level is constituted de novo. Instead, you have suppliers at various levels, and it is that sort of upward and outward flow of materials, energies, and subunits of possible function which can run such a feasible homeokinetic universe of systems. To capture the essence of a system, one defines the equation of state, which identifies how the conservations across this system are related in an invariant way. Simple system equations of state are in terms of these 3 or 4 physical conservations. Also corresponding to each conservation, there is an equation of change for the dynamic field. In complex systems, the conservations are a bit transformed. The internal state of the complex system, for example an organism, is characterized by the fluxes and potentials that drive and are driven by the engines in a cyclic manner akin to limit cycle behavior. Included as an essential part of this homeokinetic regulation scheme is an ensemble of active catalytic switches, themselves comprising thermodynamic engine parts, which by inhibition or release from inhibition shift the operating points of the engine cycles. As a result, the internal state space is mapped by a ring of operational modes which control the activity of the complex system. Here's our atomism with its fluxes and potentials. As described earlier, there are internal processes going on. It is embedded in the Earth's environment that affords various driving potentials, and we can see the cyclical nature of those. Energy is conserved. The energy and flow of energy through the atomistic states remains energy and the flow of energy. But we have discussed that there are internal ways to store that energy. In particular, in complex systems, there's a characteristic energy which is stored in the atomism, and there's a characteristic factory day flow of energy passing through the atomistic system. For example, in the human organism, the characteristic energy stored in that organism is about 600,000 kilocalories of energy. The characteristic factory day energy when the Earth day is taken to be the factory day is about 2,000 kilocalories per Earth day. Mass is conserved. There is a characteristic mass and distribution of mass species and a characteristic flow of a variety of mass species per factory day in the organism. In simple systems, it was perhaps one or a few mass species. In living organisms, those mass species are carbohydrates, oils or fats, proteins, water, ions, some salts and minerals, etc. The chemistry in the human corresponds as a rough average to 130 pounds of ingredients and to the factory day flow of those ingredients which will burn or oxidize in net and produce 2,000 kilocalories each factory day. What is the material flow? A little more than 1/2 pound of carbohydrates, 2 ounces of fat, 2 ounces of protein, a quarter or 2 of water, and a pound of oxygen each day. The byproducts emerge as carbon dioxide, urine, and feces. Momentum is conserved. Momentum, the result of the pair-by-pair collisions representing forces which change momentum, is transferred in complex systems into action that emerges from the complex factory day of the rapidly colliding atomisms. Action is the energy-time product. What emerges is their organized actions rather than the itsy-bitsy changes in momentum from collisions at simpler levels. From cells banging into cells, we see their complex, slower biochemistry emerging. From that system level, we see organized actions throughout the organs. From thence, we see the organized actions of the organism. From them, we see the organized actions of the social group. We should recognize most of these actions as transactions. Each level is made up of the organized momentum-like characteristics of lower atomistic processes. That is all there is. Each factory day or level has to be attended to by its physics, by its conservations. As one runs through the entire gamut of such factory days, one finds an entire cascade spectrum of energetic processes. Energy flows through, transforms level to level. To study a system, Iberall suggests first, choosing your field and scale of observation. Concepts of science are reduced or replaced by operations necessary to measure them. Secondly, learn all the possible directions you are free to explore, the inhomogeneity of levels and columnar chains that seem to interact to produce form and function. That vertical array of influences carry the few physical forces that create the beings, their states, and their becomings, their rates of motion and change. The concept of hierarchical recursion holds that a predictable set of conservation-driven dynamical processes and design principles will be found to recur in nature at all mappable scales of atomistic and molecular association, from the cosmos itself to the most minute leptons and quarks. The principle of hierarchical recursion is physically driven by homeokinetics, the observed tendency of all complex systems to seek essentially stability or auto-regulatory immunity against environmental vicissitudes and challenges through extensive internal thermodynamic coupling and cooperativity of such engine processes. Such self-regulatory cooperativity is found to occur both horizontally within individual organizational layers of a complex system, essentially as mechanical or chemical processes, and vertically between adjacent layers of a hierarchical system, essentially as thermodynamic processes.